All right, buckle up, everyone, because today we're diving headfirst into the world of chaos mathematics.
Sounds exciting.
Yes, we've got a ton of really interesting sources lined up, and I, for one, can't wait to see where this chaotic journey takes us.
I'm with you there.
You know, it's kind of funny when you think about it that something called chaos actually comes from systems that are deterministic, meaning they follow specific rules.
Right, exactly.
But then somehow they still manage to end up with unpredictable behavior.
Yeah, that's the really intriguing part about chaos, isn't it? It's that tension between determinism and then unpredictability.
Hmm.
We're so used to thinking in linear terms,
Yeah.
assuming that like small changes lead to small effects.
Right, right.
But chaos just throws that whole idea right out the window.
Whoosh, gone.
Yeah,
It's
exactly.
like that butterfly effect, right? Like
Oh yeah.
a butterfly flapping its wings in Brazil can cause a tornado in Texas. Is that really what the butterfly effect is all about?
Yeah, the butterfly effect, it's a really powerful way of illustrating sensitive dependence on initial conditions,
Okay.
which is, it's like a hallmark of chaotic systems.
Right.
Tiny, tiny changes early on, they can cascade into these like dramatically different outcomes later.
Yeah.
It's why like predicting the weather accurately over long periods it's so challenging.
So chaos isn't just randomness then, right?
No, not at all.
It's something much, much more subtle and complex.
Definitely.
It's like this hidden order within the seeming disorder.
Yeah, exactly.
And, apparently this chaotic behavior pops up in some pretty unexpected places.
Oh yeah, in all sorts of places.
I read that even the calling rhythms of Japanese tree frogs have a chaotic element to them.
Absolutely. Chaos, it's not just confined to, weather patterns or things like that.
Right.
We see it in animal populations, the dynamics of financial markets.
Oh, wow.
Even the beating of our own hearts.
Oh, really?
It's fascinating.
That's incredible.
What's fascinating is that despite this diversity, right?
Yeah.
There are these underlying mathematical structures that actually connect these seemingly disparate phenomena.
Okay, I am definitely intrigued,
Good.
but before we get too far along in the example,
Uh-huh.
let's maybe take a step back
Okay.
and make sure that we're all kind of on the same page.
Right.
You mentioned phase space a little bit earlier.
I did.
Could you maybe unpack that a bit more for me?
Yeah. So imagine a multidimensional space where each point represents a possible state of our system.
Okay.
That's phase space.
Right.
Think of it like a map of all the possible configuration. It's kind of like a choose your own adventure book with like infinite pages.
Oh, I like that analogy.
Yeah.
Yeah. So within this phase space, then we have these special points called fixed points, and that's where the system kind of like settles down and stays put, right?
Exactly.
Like a ball rolling to the bottom of a valley or something.
Exactly. But not all fixed points are created equal.
Oh.
Some are stable, like that ball at the bottom of the valley.
Yeah.
If you nudge it slightly, it'll just roll back to its resting spot.
Right.
But others are unstable, like balancing a pencil on its tip.
Okay.
The slightest disturbance will send it, toppling over.
Makes sense.
Yeah.
And then there are the saddle points too, right?
Oh, saddle points, yeah.
Those are the really tricky ones.
Tricky ones, yeah.
It's a mix of stable and unstable.
Right, a mix of both.
Kind of like, I don't know, trying to stand on a beach ball.
Yeah, something like that.
Yeah. But you mentioned earlier that chaos requires more than just a couple of dimensions.
Yes.
Why is that?
So simple systems like those that are described by first order equations, they're kind of limited in their behavior. They might oscillate or approach a fixed point,
Okay.
but they can't exhibit true chaos. Chaos requires more degrees of freedom, more dimensions in our phase space for those like intricate, unpredictable patterns to emerge.
Okay. I think I'm starting to get the gist of it.
Good.
So now let's dive into one of the most famous examples of chaos.
Sure.
The Lorentz system.
The Lorentz system, yes.
I hear it has something to do with weather prediction, right?
Yes. Edward Lorenz, a meteorologist, he was trying to model weather patterns on his computer back in the 1960s. And he stumbled upon something truly remarkable. Even tiny changes in the initial conditions of his model led to these dramatically different weather predictions.
Wow, so he was trying to predict the weather and accidentally stumbled upon chaos.
That's one way to put it.
That's an incredible discovery.
It really is.
What did this chaotic behavior even look like?
So his simplified atmospheric model
Yeah.
generated this stunning visual representation,
Okay.
the Lorentz attractor.
Oh.
It's this intricate butterfly-shaped structure in three-dimensional space.
Wait, so this butterfly shape is actually representing chaotic weather patterns.
Yeah.
No way.
How does that even work?
So the Lorentz attractor, it's a fractal, meaning it has this repeating pattern at different scales. If you zoom in,
Yeah.
you keep seeing the same butterfly shape over and over again.
Oh.
It's like this beautiful visual metaphor for the complexity that can arise from seemingly simple rules.
That's pretty mind-blowing. So this Lorentz system with its beautiful butterfly-shaped attractor,
Right.
this is a prime example of chaos in action.
Yeah, definitely.
And it all boils down to this sensitive dependence on initial conditions.
What other examples of chaotic systems should we explore?
Well, let's see. There are so many fascinating examples.
Yeah.
The Lorentz system it's a fantastic illustration,
Oh.
how chaos can manifest in these like unexpected ways.
Yeah.
It's a reminder that even systems that appear simple can harbor this like incredible complexity.
Right.
But the beauty of chaos is that it's not limited to these like theoretical models.
Oh, okay.
We see it all around us in the real world.
Okay, so we've got this theoretical model with the weather patterns.
Right.
But you're saying chaos exists in more like tangible systems too.
Yeah, exactly.
Okay, give me an example.
Okay, so imagine a water wheel with cups that leak.
Okay.
So water flows into the cups from above.
Uh-huh.
It leaks out at a certain rate,
Okay.
and the wheel spins.
Right.
It's a simple mechanical system, right?
Yeah, totally.
Yet its behavior can become surprisingly complex.
A leaky water wheel.
Yeah,
It does sound kind of chaotic already.
a little bit, yeah.
But I'm curious, how does chaos actually play out in this scenario?
So the way this wheel spins, right?
Yeah.
It's incredibly sensitive
Yeah.
to the initial distribution of water among the cups.
Oh.
Even the slightest difference in how that water is like initially placed
Mm-hmm.
can drastically alter the wheel's rotation pattern. It's really a captivating visual demonstration of sensitive dependence on initial conditions in action.
So if you were to like set up two seemingly identical water wheels,
Yeah.
but with just a tiny difference in how the water is distributed,
Right.
they could end up spinning in like completely different ways.
Yeah, absolutely.
That's remarkable.
It is.
It sounds like the butterfly effect on a water wheel.
Exactly.
Yeah.
The chaotic water wheel, it highlights how even these seemingly simple systems
Yeah.
can exhibit this unpredictable behavior
Right.
due to this sensitivity to initial conditions. But the beauty of chaos is that we have tools to analyze and understand these complex systems.
Okay, I'm ready to dive into those tools.
All right.
You mentioned something about Poincaré maps earlier.
I did, yes.
What are those all about?
So Poincaré maps are this brilliant way to visualize and understand the behavior of dynamical systems, especially chaotic ones.
Okay.
So imagine taking a multidimensional system
Uh-huh.
and slicing through it with a plane.
Okay.
A Poincaré map essentially captures the points where the system's trajectory intersects this plane.
So instead of looking at the system's entire trajectory
Yeah.
in all its complex glory,
Right.
we're focusing on these specific points of intersection.
Exactly.
It sounds like a way to simplify things, like taking snapshots.
Yeah, like snapshots.
Of a complex dance routine or something.
Exactly. And by looking at those snapshots, we can glean insights into the underlying dynamics of the system. For example, if the Poincaré map shows this like scattered cloud of points,
Okay.
that suggests chaotic behavior.
Okay.
On the other hand, if the points form this like regular pattern,
Right.
it indicates more predictable, periodic behavior.
It's like decoding a secret message hidden within the chaos.
Yeah, that's a good way to put
By
it.
analyzing the pattern of these snapshots, we
Yeah.
can start to understand the underlying order or lack thereof.
Exactly.
So Poincaré maps give us this visual representation.
Right.
But are there any numerical tools for analyzing chaos?
Yes. That's where Lyapunov exponents come in.
Okay.
So they quantify the rate at which nearby trajectories in phase space diverge from each other.
Okay.
It's like measuring how quickly two balloons initially close together drift apart in the wind.
Okay, that's a vivid image.
Yeah.
So a high Lyapunov exponent means those balloons are separating rapidly,
Right.
indicating chaotic behavior.
Yes.
What about a low Lyapunov exponent?
A low Lyapunov exponent suggests that the trajectories are staying close together,
Okay,
indicating more predictable behavior.
gotcha.
Think of it as a measure of the system's sensitivity to initial conditions.
So Poincare maps provide a visual snapshot of chaos,
Yeah,
while Lyapunov exponents give us a numerical measure of its intensity,
exactly.
like having two different lenses to view the same fascinating phenomenon.
Precisely. And, these tools, along with others, have allowed us to uncover this remarkable feature of chaotic systems, universality.
Okay.
It refers to the observation that certain characteristics of chaotic systems are independent of the specific details of the system itself.
Hold on, universality.
Universality, yeah.
You're telling me that chaotic systems, as diverse as they are,
Yeah,
share some underlying similarities.
I do.
How is that even possible?
It's this profound concept that points to the existence of these deep mathematical structures governing the transition to chaos across various systems.
Okay.
One of the best examples of this is the period doubling route to chaos,
Okay.
often illustrated by the logistic map.
Right, the logistic map, that
Yeah.
that simple equation
Yeah.
that models population growth
Exactly.
with limited resources, right?
Exactly.
I remember you mentioned it earlier.
Yeah.
How does it showcase universality?
So the logistic map it's this simple equation,
Right.
but it exhibits this surprisingly complex behavior
Okay.
as we tweak a parameter in the equation.
Yeah.
The system undergoes this series of transitions,
Okay.
with the population oscillating between these stable cycles of different lengths.
So population might settle into a stable pattern
Yeah,
and then suddenly double its period
Exactly.
and then double it again and so on.
exactly. And here's where it gets really interesting.
Yeah.
As we keep tweaking this parameter, these period doublings,
Yeah.
they happen faster and faster, eventually leading to this chaotic regime
Uh-huh.
where the population fluctuates erratically.
So it's like the system is losing its stability.
yeah.
And kind of descending into this chaos.
Yeah, exactly.
But you said this is connected to universality.
Right. So the truly remarkable thing
Yeah.
is that the rate at which these period doublings occur
Uh-huh.
is the same for a wide range of systems,
Right.
not just the logistic map.
Wow.
This rate is captured by the Feigenbaum constant,
Okay.
which is approximately 4.6692.
So this Feigenbaum constant is like a universal fingerprint of chaos.
Yeah, that's a good way to put it.
A mathematical signature that pops up again and again in different systems.
Exactly. It's a testament to the interconnectedness of these seemingly disparate phenomena and the power of mathematics to reveal these hidden patterns within the chaos.
Oh.
But the logistic map isn't the only example of universality in action.
I'm all ears. What other examples showcase this intriguing phenomenon?
Okay, so let's shift gears from population dynamics to the world of electronics.
Okay.
There's a simple circuit
Okay.
called the driven RLC circuit
Right?
that's often used to illustrate chaotic behavior.
RLC circuits. Those are the circuits with resistors, inductors, and capacitors, right?
Yeah.
Okay. But how can a circuit be chaotic?
Yeah.
It seems like they should just follow predictable rules.
You would think so, wouldn't you?
Yeah, like turning a light switch on and off.
But even these simple circuits can exhibit remarkably complex behavior.
Really?
Yeah.
Yeah.
When driven by an external alternating current,
Uh-huh.
the RLC circuit can display a range of behaviors,
Okay.
including the same period doubling cascade we saw in the logistic map.
Wait, so we're seeing the same pattern of period doubling leading to chaos
Yes.
in both a simple population model and an electronic circuit. That's incredible. It really highlights how universality connects these seemingly unrelated fields.
It really is. It's a testament to the power of mathematical principles to transcend disciplinary boundaries
Right.
and reveal these deep connections in the natural world.
Wow.
But the examples don't stop there.
Okay.
let's delve into a realm that might surprise you.
Okay.
The dynamics of heart cells.
Heart cells.
Ah,
I know chaos is important to understanding like heart arrhythmias and stuff,
right.
but tell me more about how it plays out at like the cellular level.
So imagine a single heart cell
Okay.
rhythmically contracting and relaxing,
Yeah.
keeping that steady beat that we all rely on.
Right. Right.
Researchers have found that under certain conditions,
Uh-huh.
the behavior of these heart cells can be modeled by equations that exhibit chaotic behavior.
So the very cells responsible for our heartbeat
Yeah.
can become chaotic.
They can.
That's both fascinating and a little bit unnerving.
It is. It is. It highlights this delicate balance within these biological systems.
Yeah.
This constant interplay between order and chaos
Yeah.
that keeps our hearts beating reliably,
Mhm.
and understanding this interplay is crucial for developing effective treatments for heart conditions.
That makes sense.
Yeah,
This is also fascinating.
I know, right?
We've gone from weather patterns to water wheels
Yeah,
to electronic circuits to heart cells.
it's amazing.
It seems like chaos is everywhere we look.
Indeed. And that brings us to another captivating aspect of chaos.
Okay.
Its potential for practical application.
Oh, okay.
Did you know that researchers are exploring ways to harness chaos for sending secret messages?
Wait, sending secret messages using chaos.
Yes.
That sounds like something straight out of a spy movie.
I know it does, doesn't it?
Tell me more.
So it's this fascinating area of research that leverages the unpredictable nature of chaotic systems to encode and transmit information securely.
Okay, I'm intrigued,
Yeah.
but I'm having trouble wrapping my head around like how this would even work.
Sure.
How can something as unpredictable as chaos be used for communication?
So the key lies in synchronization.
Right.
Imagine two chaotic systems
Uh-huh.
that are perfectly synchronized, meaning their trajectories in phase space
Yeah.
stay in lockstep with each other,
Right.
even though their individual behavior is unpredictable.
So it's like two dancers moving in perfect harmony,
Yeah, that's a great analogy.
even though their individual steps are seemingly random.
Exactly.
Okay.
Now, imagine one of these synchronized systems is the transmitter,
Uh-huh.
and the other is the receiver.
Okay.
The transmitter encodes a message within its chaotic signal,
Okay.
and the receiver, being synchronized, can extract the message,
Yeah.
even if the signal is masked by noise or interference.
Right. It's like having a secret language
Yeah.
that only those with the synchronized systems can understand.
Exactly.
And all thanks to the magic of chaos.
The magic of chaos, exactly.
That's amazing.
Researchers have actually built electronic circuits that demonstrate this principle in action.
Really?
Yeah.
Yeah.
One circuit acts as the transmitter,
Okay.
encoding a message within its chaotic signal,
Right.
and the other acts as the receiver,
Yeah.
successfully decoding the message,
Wow.
even in the presence of noise.
So it's not just a theoretical concept.
Mhm.
It's something that's been demonstrated in the real world.
In the real world, yeah.
That's incredible.
It is.
It makes you wonder what other practical applications of chaos are just waiting to be discovered.
Yeah.
It seems like we've only just scratched the surface here
Yeah, there's so much more.
of what's possible with chaos theory.
Definitely.
We've talked about water wheels and circuit, even heart cells exhibiting chaotic behavior.
Yeah, it's amazing.
Are there any other areas where chaos makes a surprising appearance?
Oh, absolutely. One area that you might find surprising is evolutionary game theory.
Evolutionary game theory.
Yeah.
Okay, I'm vaguely familiar with game theory, like
Yeah.
the prisoner's dilemma and all
Yeah,
that.
right.
But how does chaos enter the picture when we're talking about evolution?
So imagine a population of organisms
Right.
competing for resources.
Right.
Each organism has a particular strategy
Right.
for interacting with others.
Right.
And these strategies can be thought of as different players in a game.
Okay.
As these organisms reproduce and interact,
Uh-huh.
the frequencies of different strategies in the population change over time.
So it's like a game where the rules are constantly evolving
Yeah, in a way.
based on the strategies that are most successful.
Right, exactly.
I could see how that could get complex. But where does chaos come in?
So under certain conditions,
Okay.
the dynamics of these evolutionary games
Why?
can become chaotic, meaning that the frequencies of different strategies in the population
Yeah.
fluctuate unpredictably over time.
So even in the realm of evolution,
Yeah.
where we might expect some sort of like predictable progression,
Yeah, you'd think so.
chaos can throw a wrench in the works.
Exactly. It's a reminder that even in systems that seem to have this like clear direction,
Yeah.
there's always room for the unexpected.
Always.
Now, before we wrap up our deep dive here,
Okay.
I want to circle back
Sure.
to one of the most iconic images in chaos theory,
Okay.
the Lorenz attractor.
Right.
Remember, it's that beautiful butterfly-shaped structure that,
Yeah.
that represents the chaotic behavior of Lorenz's weather model.
Of course.
Yeah,
The
black.
butterfly effect visualized.
Exactly.
Yeah, it's such a striking image.
It is.
But beyond its like aesthetic appeal,
Yeah.
what insights does it offer into the nature of chaotic systems?
So the Lorenz attractor, it beautifully captures several key features of chaotic systems.
Okay.
First, it's a fractal,
Right.
as we discussed before.
Right, right.
This means it has this repeating pattern at different scales.
Yeah.
If you zoom in, you keep seeing the same butterfly shape,
Yeah.
highlighting this like infinite complexity within these systems.
Like a never-ending kaleidoscope of chaotic patterns.
Yeah, it really is.
What else does the Lorenz attractor tell us?
It also showcases this concept of strange attractors. These are attractors that are bounded,
Yeah.
meaning that trajectories in phase space stay confined within a certain region,
Right.
but they're also non-periodic,
Right.
meaning that those trajectories never quite repeat.
So it's like a dancer exploring every possible move within a confined space,
Yeah, that's a great analogy.
but never repeating the same sequence.
Yeah.
It's a mesmerizing dance of chaos,
It is.
forever exploring new possibilities.
Absolutely. And lastly, the Lorenz attractor.
Hmm.
It highlights that sensitive dependence on initial conditions.
Right.
Even the smallest change in the starting point can lead to vastly different paths
Yeah.
along the attractor.
Yeah.
Just like that butterfly flapping its wings in Brazil, potentially causing a tornado in Texas.
It's incredible.
Yeah.
The Lorenz attractor truly is a visual masterpiece,
It is.
a testament to the beauty and complexity that can arise from simple deterministic rules.
Absolutely.
It's a reminder that chaos isn't just, random, unpredictable behavior,
Right.
but rather this fascinating and fundamental aspect of the world around us.
It certainly is.
And remember, despite its seeming unpredictability,
yeah.
chaos isn't entirely without order.
No, not at all.
We've seen how tools like Poincare maps and Lyapunov exponents allow us to analyze these systems.
Right.
And the concept of universality reveals these hidden connections between seemingly disparate phenomena.
Yeah, exactly.
This deep dive has been an incredible journey.
It has.
We've gone from the basics of phase space and fixed points
Yeah.
to the mind-boggling concepts of universality and strange attractors.
It's a lot to take in.
It is. and along the way, we've explored how chaos plays a role in everything.
Yeah.
From weather patterns to the evolution of species.
I know, it's
I
amazing.
think it's incredible.
It's been a pleasure exploring this captivating world of chaos mathematics with you.
Likewise.
This field is constantly evolving with new discoveries and applications emerging all the time.
Yeah.
Who knows what other secrets chaos holds waiting to be unlocked.
It leaves me wondering if even simple systems can be chaotic. What does that tell us about the complexity of the world around us? From the intricate workings of our brains to the vast expanse of the cosmos.
That's a profound question,
Yeah.
and one that scientists and mathematicians continue to grapple with.
I agree.
The study of chaos reminds us that even in a universe governed by laws, there's room for surprise, unpredictability,
Yeah.
and endless fascination.
Well said. And on that note,
Yeah.
we've reached the end of our deep dive.
It has been a journey,
It has.
for sure.
I hope you've enjoyed this journey into the captivating world of chaos mathematics as much as we have.
I have.
Until next time, keep exploring, keep questioning,
Yeah.
and keep embracing the beautiful chaos that surrounds us.
That's a good way to put it.
Yeah.